Thank you, Louis, for this very kind introduction and for the invitation to speak at this great event. So yes, quantum sensing. I mean, in the year of quantum technologies, of course, there's a lot of talk about quantum computing and that sort of stuff, which takes all the headlines. But that's not what I'm going to talk about. I'm going to talk about quantum sensing, because quantum sensing is here and now, and it's already being applied and changing the world around us. And in the world of metrology, we've been using quantum mechanics for the last 70 years to really transform how we make measurements. So I'm going to talk you through some of the things we do as a national metrology laboratory. So measurement, as you all know, is all around us. It really affects every part of our daily life, from the way we trade, from the science we do, from our health and life sciences. Everywhere, measurement underpins all these kind of things. And it's often unknown because it works very well. And that's due to metrology and the measurement system which underpins all these measurements. And for example, NPL as a laboratory does a lot of work with CTBTO on the measurement of, for instance here, radiocrypton for monitoring Fukushima, and radio xenon for looking at nuclear explosions. And by improving these measurements, we can improve the way we study these effects. So one of the quotes we often use in metrology is this quote of Lord Kelvin, which says that arguably the ability to measure physical properties accurately has tremendous survival that gives humans adaptive evolution advantage. Well, really what it means, if you can't measure it, you can't make it any better. And that's really sort of our motto of the way we work. And of course, measurement standards and measurement has got a very long history. It started off with the Egyptians when they were building the pyramids and having a cubit. But things really changed around the French Revolution when, after that, the metric system was introduced. And in 1875, 17 countries signed what was called the Meter Convention, which really sort of started to use the metric system, particularly the meter and the kilogram, as a way of measurement. And the International Measurement System is one of the oldest international organizations in existence. It has been underpinning measurements forever and a day. And there you can see when it was signed in Paris in the French ministry, which is a room almost as impressive as this one. But measurement systems evolve, they don't stand still. Measurement systems have to adapt to new technologies and new requirements from industry. So in 1960, the System International measurement system was introduced, originally with 6 base units: the kilogram, the second, the meter, the ampere, the Kelvin, and the candela. And then in 1967, the second was redefined in terms of atomic frequency, and I'll talk about that later. And so on. As chemistry evolved, the mole was added to the SI system. In 1983, the meter was redefined in terms of the speed of light. In 1990, the quantum electrical standards came around. And in 2019, there was a big change of the international measurement system, which I'll mention in a minute. And so you can see this system adopts as we develop our science, as we develop the requirements for what we do. And why do we need an international measurement system? Well, first of all, it needs to be stable, so we can look at measurements over very long periods of time and spot trends in the measurements. So this is a picture of the CO2 in the atmosphere, which is measured over a period of about 70 years now. And we can really see that, of course, CO2 is increasing. It also means that if we have a measurement system, we can make comparable measurements. So we can compare measurements in different parts of the world with each other. This is a plot of air pollution in Europe. And basically, you can compare different sites to each other. And then an international measurement system has to be universal. So you can combine different types of measurements to make models and forward predictions, for instance, to predict the weather. And of course, it's also very important, all this measurement data which is input into AI models, what we spoke about earlier this morning. The AI is only as good as the data you put in it. And so validating the measurement data which go into AI models is crucially important. And so we constantly strive to improve the uncertainty in our measurement system. And so in 2019, after decades of research, the International Measurement System was changed to become a system which is defined in terms of fundamental constants of nature. So 4 of the base units were redefined in terms of those units. So the kilogram is no longer the kilogram which is held in a vault in Sèvres in Paris, but the kilogram is now related to Planck's constant. And equally, the Kelvin is now related to the Boltzmann constant, the ampere to the electron charge, and the mole to Avogadro's number. And this is a very important change, because this means that you can realize a measurement unit anywhere in the world, because the constants are universal, they're everywhere, they're unchanging, we believe, and so you can realize these units everywhere. So it's a true democratization of the SI system. And quantum technology and quantum mechanics has played a crucial role in this change. And we celebrated the meter convention a few months ago on the 20th of May, which is World Metrology Day in Paris at UNESCO, because it's exactly 150 years ago since the meter convention was signed. So if we talk about, going to talk about quantum mechanics, it's useful to just recap what came before quantum mechanics, and of course that's classical mechanics, and Newton is one of the most well-known protagonists of classical mechanics. He sort of proposed the theories of gravity, light, and calculus, and basically classical mechanics is very good at describing the world around us, how we perceive it. By the way, the picture there is a picture of Newton's apple tree, which is in the garden of MPL in the UK, which is grown from a graft of the original Newton's apple tree in Lincolnshire. And you can, on the side there, you see a little corner of our new Quantum Metrology Institute, where we do some of the most forward-looking measurements. Lord Kelvin, again, in 1900, he said that after classical mechanics, there was nothing more to discover in physics. Everything was well known, and all we needed to do was make more precise measurements. And of course, he was wrong. Classical mechanics couldn't explain a number of the observations in science, particularly black body radiation, the photoelectric effect, and the hydrogen spectrum couldn't really be explained by quantum mechanics, by classical mechanics. And that's when quantum mechanics was born. And we chose 2025 as the year to celebrate 100 years of quantum mechanics. Now, of course, quantum mechanics wasn't discovered in 1925. There were many developments which led to the birth of quantum mechanics, but 1925 was chosen because a number of important papers came out around that time. Now, I'm not going to explain the whole of quantum mechanics. I mean, a half-hour talk is not really long enough for that. But I'll mention some of the key characteristics which are important to realize. So the world of quantum is quite strange and counterintuitive. And one of the first things, of course, you always learn about quantum mechanics is the wave-like nature of particles. And the wavelength of particles is given by this very simple equation, the Broglie wavelength. And the Broglie wavelength is Planck's constant over momentum. And here, if you look at Planck's constant, it's a very, very small number. It's 10 to the minus 34. And that really means that to see quantum effects, you have to look at a very small scale. It explains why a cannonball is classical and why an atom is behaving like a quantum mechanical property. Because for an atom, you can sort of reach that sort of length. The next important thing about quantum mechanics is that things are quantized. So it's like the strings of a guitar. It can only play certain notes. Only certain energies are allowed in certain systems. The next one is superposition. So this means that particles, for instance, in a double slit experiment, behave like waves. They interfere with each other, or they interfere with themselves. And the particles basically looks like they take multiple paths to the screen. And I think the next keynote will speak in more detail about this. And the final one is entanglement. So entanglement means that properties can have non-local characteristics. So particles which are in a quantum state, they sense each other. Measuring one particle immediately determines the state of the other particle, and it doesn't matter how far apart they are. And this is a really counterintuitive effect. So in quantum mechanics, in summary, things can be in two states at the same time. Things are described by probabilities. The act of actually measuring something has got a profound effect on the outcome. Properties are non-local, and it's impossible to know everything at the same time. Basically, Heisenberg's uncertainty principle. And yet, quantum mechanics is the most successful theory. It describes exactly how nature behaves around us. And so it's incredibly, incredibly powerful. And of course, there's many applications of quantum technology all around us, which we've lived it for many years. NMR, the laser, nuclear power, semiconductors, atomic clocks, they all are based on these principles of quantum mechanics. So how do we reach the quantum regime? Well, you saw the Broglie wavelength is very small, so we have to make things very small. So we use things like nanofabrication to make very small structures where we can trap individual electrons or ions. We can build things from the bottom up, for instance, using an optical lattice and putting ions and atoms into that lattice. We also have to make things very cold. We have to get over the Brownian motion. So we use things like dilution refrigerators to go down to almost absolute zero. I mean, this is an instrument which goes to a few millikelvin, a few thousandths of a degree Kelvin, and that's where you can really start to observe these quantum effects. Now, you don't have to use cryogenic liquids. There's also a technique which allows you to cool things in a different way, which is called laser cooling. You basically shine lasers onto a cloud of atoms, and these lasers pass a small amount of momentum to the atoms and thereby slow them down. So it's a little bit analogous to shooting tennis balls to an airplane. If you shoot enough tennis balls, you can actually slow the airplane down. And this is a way in a high vacuum system to realize nanokelvin temperatures of small clouds of atoms or ions, which is a very powerful technique to realize this quantum regime. And this can now be done readily in the laboratory and in other applications. So let's start with looking at atomic time. So before atomic time, there was ephemeris time related to the rotation of the Earth. So a clock is basically a reference, in this case the rotation of the Earth, and an oscillator, in this case a grandfather clock, which gives you an exact sort of frequency. In 1955, Louis Essen at MPL developed the first cesium clock, basically a clock based on a transition in a cesium atom. And this clock was immediately 1,000 times more accurate than a traditional clock. And the way an atomic clock works is very simple, very similar to an old-fashioned clock. You have a reference, in this case it's a cesium atom, and you have an oscillator, in this case a microwave source, and you link the microwave source to a transition in the cesium atom. In this case it's the hyperfine transition of the cesium atom. And because every cesium atom in the universe is the same, they've all got the same transition, you can build this clock with the same frequency everywhere. And so this frequency turns out to be 9.1 gigahertz, so a second is 9.1 billion oscillations of this microwave. And that's how you make an atomic clock. And atomic clocks are very important for our modern society. They underpin lots of technology, for example, GPS. It's the way we all got here this morning, using Google Maps. It's based on very accurate timing signals from atomic clocks. Now at MPL we work on the next generation of clocks, and they are optical clocks. And it's actually the same thing. So you use, again, an atomic species, strontium, ytterbium or aluminium, and you use an optical frequency standard. So in this case that would be a highly stabilized laser. And because the energy transition of an optical transition is higher than a microwave one, this clock ticks 10,000 times faster than a microwave clock. And so there is the potential to make this clock much more accurate than the traditional cesium clocks. And this little plot here shows the progress of the uncertainty in atomic clocks, these are microwave clocks, over the decades. And you can see we make these clocks more and more accurate. And at the moment, the best cesium clocks are operating at about 10 to the minus 16 seconds. But then you've got the optical clocks, and you see they were developed a bit later, but they're coming down much quicker. And at the moment, the most accurate optical clocks, they are accurate to 1 part in 10 to the 18. And 1 part in 10 to the 18 is 1 second in the lifetime of the universe. So if you set this clock ticking at the beginning of the universe, it'd still be within a second now. That's an incredible accuracy which you can achieve with these atomic quantum clocks. Another field where quantum has made a tremendous impact is in electrical metrology. In 1962, Brian Josephson predicted it's now called the Josephson effect. Of course, it wasn't called the Josephson effect when he discovered it. But this is an effect where you have two superconductors which are joined via a very small insulating barrier. And this insulating barrier is only about 100 nanometers thick. And that means in quantum mechanical terms, superconducting electrons can tunnel through this barrier. And when you illuminate this barrier with microwave radiation, the junction creates a voltage. And this voltage is an integer times Planck constant over 2 times the electron charge times the frequency with which you irradiated. And this is really very interesting, because here you've got a voltage which doesn't have any material parameters in. It's only got 2 fundamental constants of nature, the electron charge and the Planck constant. And there are no material parameters, no dimensional parameters. So this is a way where nature gives you a voltage standard just like that, without you having to create it. And this has transformed the field of electrical metrology. It made electrical measurements 1,000 times more accurate than before, when it was based on voltage cells. And similarly for resistance, in 1980, Klaus von Klitzing discovered the quantum Hall effect. And this is an effect where you put a thin semiconductor in a very high perpendicular magnetic field, and you measure the Hall voltage, the perpendicular voltage on this barrier at very low temperatures. Again, the resistance of this device is Planck constant over the electron charge squared. Again, there's no material parameters, only those 2 fundamental constants. And again, this is a way of realizing a quantum standard very straightforwardly. So there's also talk now about using things like superposition and entanglement within measurement. And this is sometimes called the second quantum revolution. And I'll show you a few examples of that. The first one has been around for quite some time. It's called the SQUID. It's a superconducting quantum interference device. So it's basically a superconducting ring with 2 of these Josephson junctions in it, 2 of these insulating barriers. So what you're making here is an interferometer for superconducting current. And if you vary the magnetic field which this SQUID senses, then you get oscillating voltages out of this device. And the period of oscillation here in magnetic field terms is 1 to 10 femtotesla. That's a very, very small magnetic field. If you look here at the scale, this is the sort of fields, magnetic fields, which are produced by your brain when neurons fire in your head. And so you can use this effect to make a sensor for signals in your brain, which is really very important to study things like epilepsy, dementia, schizophrenia, or brain trauma. And so you can really start to probe what's going on in the brain using this sort of technique. So that was done at cryogenic temperatures. You saw this person had a big cryostat on his head. You can now also do this with atomic magnetometry, where basically you have a small sample of either cesium or rubidium, and you polarize this with a laser beam, and then if it's exposed to a magnetic field, the spins start to rotate, and you can probe that with a second laser beam. So it's a little bit like a spinning top. All these atoms behave like spinning tops, and you can make very, very small magnetic sensors like that. And this you can use for, again, for monitoring the brain. You see a lady there wearing a much simpler helmet, which can measure the brain activity. But you can also test lots of materials with magnetometry. You can use it for navigation, or you can even base new forms of computing on this type of technology. The next application area is gravimetry. Gravimetry is very important. A lot of things depend on gravity, geology, climate change, satellite flight. All these things are affected by gravimetry. And originally, gravimetry is measured by, well, Newton did it by dropping an apple. These days it's done by dropping a corner cube in a laser beam. And now we can make atomic gravimeters, where we drop a cold cloud of atoms in a laser beam, and we can make interferometry with these cold atom clouds, and thereby measure gravity very locally, very quickly. And you can start to map out what's underground, which is a very important application area. And I said, these atomic clocks which we use are good to pass in 10 to the 18, and that means, of course, they are sensitive to general relativity. If you move one of these clocks 1 centimeter in height, their frequency changes by 1 part in 10 to the 18 due to the gravitational potential. And so you can start to use these clocks as gravimeters as well. And well, the Earth crust is 2.5 years younger than the crust. And this is being used to look at things like dark matter. This is how sort of quantum sensing can be used for really exciting science. So the last example I want to give you might be interesting for this community. It's a sort of byproduct of the work we've done on optical clocks. So the way to check that an optical clock is working properly is to compare it with another clock. And so we do that in Europe by comparing clocks in different laboratories. So in the UK we've got NPL, but in Germany you got PTB who built optical clocks. In Italy you got INRIM. In France you got LNE SIRT. And these locations are connected via optical fibers, and we can compare these clocks using very accurate frequencies over an optical fiber. So we have a highly stabilized laser, and we send a pulse through an optical fiber, and it goes back and forth, so we can take out the effect of the fiber attenuation. But sometimes we couldn't sort of get rid of the noise. There was a remnant signal sometimes left on our optical fiber data, and it turned out that this remnant noise was related to earthquakes. So we found out that when we were doing these optical clock comparisons, we had this noise signal there at the top left-hand side, and it actually coincided with an earthquake in Italy. And the top curve, the red one, is the one we measured on our optical fiber, and the blue one is a seismometer measurement somewhere in the UK as well. And you can see there's a direct correlation between those two. And then when we started looking more closely, actually you can relate it much more to each other. It's a very sensitive technique for looking at earthquakes. And this is important because most seismic stations are on Earth, are on land. There aren't very many on the bottom of the sea. But conversely, of course, there's an enormous amount of optical fibers in the oceans, on the seabed. And there's, this increases more and more. And quite a bit of this network is unused. And so there's the potential here to have thousands of sensors all around the globe, which measure in real time continuously. They can coexist with data. We now know that we can measure this on fibers which are used for data transfer, and we don't have to change the infrastructure on the sea floor, which would be very expensive. Besides measuring earthquakes, we also found that you can actually measure the temperature of the water and pressure, so you can start to look at many more parameters in ocean currents and looking at climate variables using this technology. And most recently, we've set up a network around New Zealand with the New Zealand Meteorology Laboratory. Of course, New Zealand is an area which is prone to earthquakes, and we've been able to detect earthquakes on that system. And this could be used as an early warning system for tsunamis, because, of course, the sooner you detect the earthquake, the earlier you can warn the surrounding population. So we think this technology will have a lot of opportunity going forward. So with that, I come to the end of my talk. Quantum sensing, it's a bit weird, but it's definitely a lot better than classical sensing. The quantum revolution, it's here and now. I mean, there are lots of startup companies developing instruments based on these principles of quantum metrology and using cold atom technology to improve sensing. And it will continue to change our lives. I mean, these technologies will be used for health and life sciences. It will be used for computing, and all these things will have a tremendous effect on what we do. So with that, I'll say thank you for your attention and finish there. Thank you.
Thank you, Professor Jansen. Quantum sensing in 25 minutes. Isn't that amazing? Right?
I skipped a lot.
The floor is open for questions. We have around 5 minutes. If you have any question for Professor Jansen, please come to the microphone. A kind reminder, on Friday morning from 9 to 10, we're going to have a panel on use of the cables that Professor Jansen was talking about for earthquake monitoring. Right, from 9 to 10, acoustic sensing, we have that. I have a question for you. It comes from the audience. And I guess it's from someone involved in on-site inspections. During on-site inspections, we have the possibility of measuring the gravity field. So the question is, what are the advantages of a quantum gravimeter compared to a traditional one like a CG6?
Yes. So with the traditional way of dropping a corner cube in a laser beam, like an FG5 or something like that, you need to average for quite some time. You need to set the system up quite carefully so that it's vertical, and then you need to take data over a certain period of time to get to your 1 part in 10 to the 9. Now the atomic gravimeter is much faster than that. Basically, it gets there in a few seconds. So you can actually scan an area, as I showed the picture, where they actually put the atomic gravimeter on a ship or on a platform, and you can move it around. So you can actually start to map out gravity to a similar level of uncertainty as what you do with the traditional one. So it's much faster. Yep.
That's great news for our surrogate inspectors.
Yeah.
Another question. I see somebody from the audience who's probably involved in the development of quantum gravimeters. From Birmingham, right? Any other question, please? I have a question for you. So when I started studying physics, and I wanted to study meteorology, not metrology.
Yeah, it's often confused.
Someone told me, will you really be called a physicist if you do not study quantum physics? So imagine that I'm a youngster asking you, Professor Jansen, why should I study quantum physics? What would you tell to this youngster?
Oh, well, these days, if you go study physics, you always study quantum physics as well, because the first year is classical physics, the second year is quantum physics. So it's virtually impossible now to do physics without doing quantum physics. I mean, it pervades everything and everywhere. So yeah, definitely study it.
So
but you don't, I mean, for a lot of applications, you don't really have to understand quantum physics. I mean, if you build engineering solutions, you just have to be aware of the principles and apply those. It's like any other technology.
You have to do it. Any question from the audience? Yeah, we have a question there, please.
Is this working? Yeah. Thank you for the talk, Professor Jensen. It was a great talk. So in your perspective, the quantum technology right now is expensive. So all the countries cannot afford, for instance, to have fiber optics to measure earthquakes. But what is your perspective about this technology and the evolution of the technology in terms of the accessibility and the capacity that countries can access to the technology to monitor what is happening on the Earth?
Yeah, so the picture showed that there's lots of fiber everywhere, but it's of course the equipment you put at the end of this fiber. And these are ultra-stable stable lasers, which are at the moment still not very easily to come by, but the engineering is moving forward and it's making it more and more compact, and certainly within the next sort of 5 years there will be small modules which you can just hook up on a fiber and have a complete system for monitoring earthquakes. So it'll become cheaper and cheaper because the technology is all there. It's just a matter of making it more engineered, smaller and cheaper.
Final question, please.
We hear in literature that about encryption, quantum secured communication. Is only scientific, or it was used in communication for encryption of information communication?
Quantum communications?
Quantum communication. Quantum cryptography.
Quantum cryptography, yeah. So yeah, quantum cryptography is being used at the moment. There are some demonstrator networks in big cities. So there's one in London, I believe there's one in Switzerland, where a number of banks have got a quantum cryptography system to communicate with each other. It's not widely used yet. It's still very much sort of in a demonstrator phase. But again, there are numerous startup companies who are building systems and starting to experiment with those.
Thank you.
And if I may add, if you are interested in quantum encryption, be here in 1 hour, because Professor Buzek is going to talk about that. That will be our second keynote on quantum physics today.
Thanks.
In 1 hour.
Brilliant.
Thank you so much, Professor Jansen. Please, a big applause for our keynote speaker.
Thank you.